Okay, class, let's look at an application here of force vectors. So this piano causes a force due to its gravity or weight straight down towards the center of the earth. There's another force that's being created against the ramp by the piano. And then there's a force required to hold this in place. And if the movers have to keep that steady, they need to supply 300 pounds of force. And so if we see that this angle for the ramp is 20 degrees, that 20 degrees is going to translate to the angle here between these forces. So what we're going to do is use the fact that this creates a right triangle because the force F2 pushing the piano up is perpendicular to the force of the piano against the ramp. And then the hypotenuse is created by the force of the gravity. They're asking us how much the piano weighs, so they're really asking us to solve for force 1 here. All right, so I'm going to leave that in place, and we're going to take and create an equation that we can solve. Okay, remember the sine in a right triangle, the sine of 20 degrees is equal to the opposite over the hypotenuse, and the opposite is the force, the magnitude of F2, and the hypotenuse is the magnitude of F1, which we consider to be the weight of the piano. Now we do know that this F2 required is 300 pounds, so we can actually substitute, and we're going to have the sine 20 degrees equals 300 over the magnitude of force vector 1. Okay, so if I solve this for F1 force, I'm going to get this would be equal to 300 over the sine of 20 degrees. Okay, and if we put that into a calculator correctly, we would get roughly a weight of 877 pounds. All right, so in this next example, we've got an object, and we call it static equilibrium if the object is at rest, and then the sum of the forces acting on it must be 0. So in this case, we've got a force applied to each of these two cables, and we've got the gravitational force of 1,200 pounds bringing it down. So if we sketch that into a force diagram here, we've got force 3 is represented by 1,200 pounds. So we know that much. We know that F3 is equal to 1,200. Magnitude of F3. Okay, and we've got a force acting on this cable in that direction. We're going to call that F2. And then this force here, F1, is the 1,200 pounds distributed between these two forces. So we're looking at F1 in the longer cable and F2 in the shorter cable. Now, we're always interested in the angle between the x-axis and the force, the vector, force vector. So we want that angle, which is 45 degrees, but we also want the sum of the 45 degrees and then whatever is going on between here and that. So if that's negative 30 degrees, this whole thing is 180 degrees halfway around the circle. And if we're going to take off 30 degrees from 180 degrees, that leaves us with 150 degrees for this angle. Now, remembering that a vector is equal to the vector's magnitude times cosine of the angle times I plus the sine of the angle times j. That's the angle made between the x-axis and the direction of the vector. And this is the unit vector in the same direction as v. Okay, so we're going to use that to identify some of these. So F1 is going to be equal to F1's magnitude times the cosine, and the angle that takes us to F1 is 150 degrees, so that's going to be cosine of 150 degrees I plus the sine of 150 degrees J. F2 it's going to be the magnitude of F2, and then times the unit vector in its direction based on the angle of 45 degrees for F2. So cosine of 45 degrees cosine of 45 degrees I plus sine of 45 degrees J. Okay, now F3 is a little different. So we already know the magnitude. I'm going to see why this is so simple, is we know the magnitude of F3. And that's going to be cosine, so that's going to be 270 degrees all the way around here. You don't really have to do this if you understand what's about to happen here. Cosine of 270 degrees plus sine of 270 degrees J. Okay, we actually know that F3, the force of F3 is the 1,200 pounds, because that's drawing down here. So we can substitute 1,200 pounds, and then the cosine of 270 is 0, but the sine is -1. So F3 is really just going to be -1,200 times J. Okay, and then what we're saying up here is that these are at equilibrium. A balance is maintained if the force that results from the sum here is 0. So here's what we need. We need F1 plus F2 plus F3 to equal 0, the 0 vector. Okay, so we're pretty much done with our pictures. I've copied our little system here, and if we simplify this a little bit, we know that F1 is equal to force of F1, magnitude of F1, and then the cosine of 150 degrees is negative square root of 3 over 2. So we're going to put negative square root of 3 over 2 and then this is times I. And then the sine of 150 degrees is 1/2. So we're going to distribute this to each term and write this as magnitude of F1 force times 1/2 J. Okay, and I'm going to do the same thing here with this. F2 would be equal to, if I distribute the magnitude of the force and calculate the cosine of 45 degrees, which is the square root of 2 over 2. And then times the I plus also the sine of the square root of 2 over 2 times j. Okay, and then F3 is just negative 1200j. Okay, so if I add these three together, so if I take this plus this plus this, I need to get the zero vector, 0i plus 0j, which is just zero vector. So we're going to take the like terms and put them together and realize that for the coefficient of I need it to sum up to 0, and then for the coefficient of j, I need it to sum up to 0. So in this case, I'm going to have to take negative square root of 3 over 2 times F1 magnitude plus square root of 2 over 2 times the magnitude of F2. And these are the parts that I'm going to add together to get the I part, which I need to be 0. So if this adds up to 0, I have 0i. And then over here on the same, by the same notion here, if I take 1/2 of magnitude F1 plus square root of 2 over 2 times magnitude of F2. And then we're also have to subtract the 1200 because we got three components that need up to add up to be 0 times j. So then we're going to put our minus 1200 here. That has to equal 0. Okay, so I've copied over the system here that we need to solve. It's the system in the magnitude of F1 and magnitude of F2. Just think of those as x and y, and it'd be like any other system. So I'm going to solve this one for F2's magnitude. So I will add the square root of 3 over 2 times the magnitude F1 on both sides. So it goes way over here, and we're going to put it over here. So we're going to get square root of 2 over 2 times the magnitude of F2 is equal to positive square root of 3 over 2 times magnitude of F1. Okay, and we want to solve for the magnitude of F2, so I'm now going to multiply by the reciprocal here to get 1. So if I multiply both by the 2 over the square root of 2, then we're going to end up with a magnitude of F2 equal to, the 2's are going to divide out. This will be a square root of 3 over a square root of 2 times the magnitude of F1. Okay, so we now have a value for F2 in terms of this equation, so we can substitute the result for F2 in the other equation. And that gives us 1/2 the magnitude of F1 plus square root of 2 over 2. And for the magnitude of F2, we'll substitute this. Square root of 3 over the square root of 2 times the magnitude of F1. And we have minus 1200 equals 0. Alright, so we're just cleaning this up now. So that's going to divide out, and we end up with this term, square root of 3 over 2, magnitude F1. And this is minus 1200 equals 0. So we're going to combine our like terms here. We know that 1/2 plus square root of 3 over 2 magnitude F1. If I add 1200 to both sides, I can write this equals 1200. Okay, so we take, if we think of this as 1 plus the square root of 3 over 2 times the magnitude of F1 equals 1200. And now if I just multiply by the reciprocal, I'll take 2 over 1 plus the square root of 3, and then I'll multiply this by 2 over 1 plus the square root of 3. Okay, and then that just leaves this as magnitude of F1 equal to 2400 divided by 1 plus the square root of 3, which is roughly equal to 878.5 pounds. Okay, and so we now have a magnitude for the force for each of those cables. If we take F1, substitute it, and we also know F3, so we can go back and get F2. And if you solve for F2 in one of your equations up there, you can get something close to 1075.9 pounds.